I'd like to do one last example of how we can take what we've learned so far and make things more interesting. I'd also like to take the opportunity to just give you a little bit of practice with graphing some of these more complicated functions in Mathematica. So what I'd like us to do are examine the horizontal asymptotes of the function that I've provided in the slide here. Now, horizontal asymptotes is just a way of saying, let's take a look at the limit as our variable is going off towards infinity and negative infinity. Vertical asymptotes, if you're wondering, are something different. Vertical asymptotes are where the denominator of your fraction here would give you a value of 0. However, we're only really interested in those limiting behaviors, so let's take a look at the limit of this function as t goes towards either positive or negative infinity. So the goal of this example is to try to take what we've learned. Instead of just having polynomials, we now have some radicals thrown into this mix. That is, we don't just have polynomials anymore, we have some cube roots in various different places. See if you can think through how to first apply what we know about polynomials and then factor in the fact that we have these 1/3 powers, or cube roots, going on, and figure out what the limit of this function would be as t is going off towards positive infinity. Take a minute, give it your best shot. I've even given you some possibilities here so that you can check your work. After you've stopped and worked through it on pencil and paper, resume the video and we'll talk about it. Now first, let me walk you through the thinking process for this particular problem. As always, we want to separate things to make everything as simple as possible and go one little bit at a time. So first, let's focus on the numerator. We've got this t to the 4/3 power, and we've got this 9t to the 1/3 power. 4/3 is larger than 1/3, and so as t is going towards either plus or minus infinity, it's this part of the algebraic function that is stronger than this part, and so we'll ignore this particular part, the 9t to the 1/3. So the numerator could be simplified by just holding on to that t to the 4/3 part. Similarly, in the denominator, first just forget about the 1/3 power and focus on the 8t to the 4th plus 2. The plus 2 is not important as t is going off towards plus or minus infinity. In fact, it's hardly contributing to the value of this thing at all. So in terms of limits, this function and the simpler function 8t to the 4th have exactly the same limit. That tells us that once we factor in the 1/3 power, or the cube root, we can first ignore the plus 2 and then just be considering 8t to the 4th all raised to the 1/3 power. And so this big bad limit as t is going towards plus or minus infinity should be exactly the same as this much easier to think about limit right here. The only thing at this point standing in between you and your final answer is algebraic simplification of this thing right here. So we had a couple different options, 0, infinity, a half, an eighth. We can figure out what these things should be from exponential rules, but another thing that we should be able to do is take a look at a graph of this function and figure out what the answer ought to be graphically. So I'd like to show you two quick ways of doing that in Mathematica. If I pop on over to my Mathematica document that I have going on, I've gone ahead and run a simple calculation, and I've gone ahead and programmed in the function that we're looking at. I'm very comfortable using the syntax of Mathematica to make my cube roots accessible through the Mathematica function cube root. Remember, I could always use a palette and look for nth roots in this way as well. But I've programmed in this function. The easiest way for me to graph this in Mathematica, especially if I'm brand new to Mathematica, is to type in that equal sign and then say, how do I graph f of t? And ask Mathematica, and Mathematica does it for me beautifully right here. Now Mathematica is going to use the word plot for the types of functions that we're going to want to see in a calculus class, as opposed to the word graph. So that can be a hard thing to remember. But I'd like to do one more thing with this graph that we have right here. If I now click on what came up from that equal sign, it'll go ahead and put the Mathematica code in for me right here. I want to ask Mathematica about the syntax of that plot command, because I do actually have the ability, just like I would on a graphing calculator, to plot more than one function at a time. Right now I'm just plotting the function f of t. What I would like to do is plot f of t along with the straight lines 1/2 and 1/8 to see if we can graphically determine what the limit ought to be for this function. And Mathematica says that in order to do that, if I want to graph more than one function, maybe 2 functions at a time, I should list those functions in between braces. So if I come down here and put braces around f of t, afterwards I could put the values of 1/2 and 1/8 in and hit Shift Enter, and now Mathematica is graphing all 3. Notice that it looks really different than it did before. Let's get rid of them again, just for a moment. That's because it's changed the axes. Before I went down to 4 and up to 6 on this axis. As soon as I put in 1/2 and 1/8, in order to see them better, Mathematica is zooming in on the y-axis, and that's why the graph got a little bit funky. Now we only go from -1/2 to 1. But we could also change the range, maybe going from -10 to 10. That doesn't really help us. Let's try going from -20 to 20. And we can keep zooming out in this way until we get a window that's helpful. And there I see it for me. The blue function is my function f of t. And we want to keep zooming out and out because we're really interested in what this function is doing the closer we get to infinity. So widening this viewpoint is really helpful. Right here, it's that 1/2 that appears to be the limit of this function, not the 1/8. Now there is an algebraic reason for that, and that's because we have to remember the rules of exponents. And it's important to note that although limits behave, exponents don't always behave. When you have the product of 2 values raised to an exponential power, you need to distribute that n to both terms on the inside of the parentheses. So it is an exponent rule that a times b, all raised to the nth power, is a to the n times b to the n. And there are many other exponent rules that are also well and good. This one, a to the nth power raised to the mth power, is a to the n times m, comes into play where we have that t to the 4th all raised to the 1/3 power. That's the same as t to the 4/3 power. It is important to keep in mind, however, that not all things that look like mathematical rules are mathematical rules. Although when we have a multiplication sign inside these parentheses, we need to distribute the nth power on that exponent. If we would have changed that times to either a plus or a minus, we would not distribute that n to both terms. So I sometimes call this the exponents do not behave rule, because just because it looks like a rule that you might want to be true doesn't mean it actually is true. These are some things that take a lot of practice to get used to, knowing what is automatically a rule and what isn't. So it's worth maybe writing them down, keeping notes with you so that you never forget.